So Abu Dhabi is here, beautiful city, very close to the super famous Strait of Hormuz. And there is a research center, Technology Innovation Institute, around 1,500 talented people working on applied research. So we don't do papers, we do products. In different verticals, we have centers on advanced materials, AI, autonomous robotics, on directed energy, quantum computing. And I'm coming specifically from the Cryptography Research Center. In Cryptography Research Center, we are around 150 people. That I can confidently say, in terms of size, is in the top 5 of largest institutions fully dedicated to cryptography worldwide. Actually, I only know other 2 institutions that have same numbers, so I could say top 3. Inside this research center, there is a smaller team that is the Privacy Enhancing Technologies team, is the one I'm leading. I think we are around 20 people, maybe 30, I never count them, but sometimes I go to the office, there is a new guy, around 30 people we are. We are working on secure multi-party computation, fully homomorphic encryption, verifiable computation, and identity and access management. Verifiable computation, I'm not talking about TIIs here, I'm talking about proof systems, so pure cryptography. No? We have 4 product lines. We have identity and access management. We have a password manager that is based on oblivious to random functions. So it basically leverages secure multi-party computation. We have identification and registration for agentic ecosystems as well. And we have 2 product lines on confidential AI, one with fully homomorphic encryption, another one with secure multi-party computation. This is the one I'm going to talk about today. I'm going to talk about PetalGuard. It's our privacy-preserving federated learning framework. So it's a platform to build AI models without sharing data. So what's the problem that it solves? It's simple. We have different entities. They have data. They want to train a model, and they cannot because of privacy regulations, because the data is too sensitive to be shared. It contains intellectual property. Sometimes it's not privacy. Sometimes the problem is size. The data is so big that it cannot be moved. It's in a data silo. And this is what requires learning, AI learning, to be decentralized. This is what federated learning does. So use cases that we have in UAE. We are in conversations with several companies. One of them is trying to do models for climate change prediction. They have environmental data from different public and private institutions in different companies, in different countries. And we are helping them in doing these models for climate change prediction. The pictures, by the way, are from Abu Dhabi. So as you can see, it's not all sand and desert. We also have some green beyond the golf courses. Also, we have a police department that wants to do model for crime prediction. So like in the movie Minority Report, same style. And they want to use data from different Gulf nations and Emirates. I think it's an easy task because there is no crime in Abu Dhabi. It's the safest country on earth, except for the Iranian drones. Then we have Emirates Health Services that wants to make a model on predicting no-shows in medical appointments. This is an issue that we have there, in which I actively contribute, unfortunately. But these are just some examples that I put here for diversity, but we are in conversations with other companies to build models, also in the defense sector. So what is confidential federated learning? What is conventional federated learning? FL was invented by Google in 2016. And the idea is very simple. I have an interactive slide that explains how it works. The idea is that you do not move the data. You train where the data is. So you have the animations are visible? Because I don't see them. Huh? Yeah, okay. You have an initial training phase in the entities. Then just instead of sending the data, you send these local updates to an aggregator. The aggregator combines these locally trained models into an aggregated model with the combined knowledge and then sends back. And then we repeat this process again and again until we have a model with sufficient accuracy. This is how federated learning works. Intuitively, we are never sending the data. We only send local updates. So we can confidently say that we are protecting the data, but in reality, this is not true, because now we know that there are very effective attacks that can be used to extract the data from the local updates. So there are membership inference attacks that are highly effective. So conventional federated learning, as it was initially designed by Google, is no longer secure. But if we go to the state of the art, we can find production-ready frameworks for federated learning there. So there are already very good frameworks out there, and they are aware of this issue. So they have to be providing some mechanisms to protect against data extraction. And I have selected two that are the most common ones that I find in literature. You can find them in Flower Framework, for example. You find these two countermeasures. First one is secure aggregation. How this works is there is an initial phase in which entities talk to each other. So they select some masks, they agree on some random masks, and then they mask their local updates so they look like random. They send these masked updates to the aggregator, and the aggregator can still combine them into an aggregated model because the masks are selected in a way that they cancel each other. So they add up to 0. There is even a version in which you can mask the aggregated model and the unmasking is done in the entity, but the concept is the same. The idea is that we make the local updates look like random, and we can do the aggregation anyway. In terms of privacy preservation, this solution is very effective. It's impossible to extract data when we use masking, but there are some complications. First problem, complex client coordination. Clients need to talk to each other. In practical scenarios, when you have thousands or hundreds of entities, not all the entities talk to each other, you have subgroups. But that also means that each entity has to trust all the other entities in each subgroup. So there is a trade-off between trust and complexity here. No? Another problem that we have is that if one of the entities does not submit the masked updates, aggregation fails because the masks do not nullify each other. There are variations in which we can solve this using threshold schemes, but that brings complexity and also a trade-off between complexity and trust. So it's not an easy problem to solve. Another issue that we have with secure aggregation is that if one of these clients sends a local update with a backdoor, we will never know. We cannot run model poisoning detection techniques on masked models. Another issue is that a rogue aggregator can do many nasty things here, and we have no way to detect it. This is the main problems that secure aggregation have, or the main limitations. Another solution that we find in the state of the art and is widely adopted is differential privacy, adding noise. So we can add noise to our local updates, send these noisy updates to the aggregator, and the aggregator adds them into a noisy version of our aggregated model. And indeed, we can add sufficient noise to these updates in such a way that model data extraction is unfeasible. But if we do that, the noise in the aggregated model becomes significant, and the accuracy gets significantly degraded. Applying DP, applying differential privacy directly on the aggregated model is a good practice. The trade-off between accuracy and privacy is acceptable, but using DP to protect the local updates is not. So it's not a good solution. So what we do in PetalGuard is completely different. We use secure multi-party computation because it does not pose any trade-off between accuracy and privacy. We can have both. The main difference that you may notice is that we do not have one aggregator, we have several. I put 3 in this example, but we could have as many as we want. The idea is that we have an initial training phase where we train our local model without sharing the data, like in conventional federated learning. But after that, we don't do masking or noise addition. We do secret sharing. So each parameter is transformed into random cryptographic shares, one per aggregator. Then we send these shares to the aggregators, and they, in a decentralized fashion, they combine them into shares of the aggregated model. Then they can send copies of the shares of this aggregated model to the entities for reconstruction. And then we can retrain again and repeat this process several times, several iterations, until we find a model with sufficient accuracy and we finish the federated learning process. So as you can see, in each iteration, we are never sending local updates, we are never sharing the aggregated model. All the things we share is random cryptographic shares that disclose no information. We have 0 data exposure, end-to-end cryptographic guarantees of privacy, compliancy by design with privacy regulations, no accuracy loss, and it's fully modular and scalable. So we can have as many entities as we want. We can also have as many aggregators as we want, and there is no performance degradation. In terms of accuracy, you can see in the left side, comparison of using MPC and not using MPC doesn't affect accuracy or loss function at all. So I'm talking about performance. What happens with bandwidth? Secure multi-party computation is famous for being bandwidth hungry. Each parameter, we have to divide it into random cryptographic shares, one per aggregator, and each one of these shares has to be encoded into an algebraic structure like a finite field or a ring. That's heavy. So it can be like something like this, scary picture. But we can use, for this specific use case, for this protocol, there are some mathematical optimizations that allows us to send shares only to one aggregator, not to all of them. To the other aggregators, we can send very small random seeds. And with these random seeds, the aggregators can generate all the shares by themselves using pseudo-random number generators. This is very important because now the bandwidth does not depend on the number of entities and aggregators, only on the number of entities, so it scales better. And it's even better than this because we can place our aggregators where the entities are. So we don't need to send any share, we only need to send the random seeds. We have basically reduced the bandwidth to nothing at the time of transmitting the shares of the local updates. Unfortunately, for submitting the shares of the aggregated model, we still need to send all the shares. There is no mathematical optimization possible there. We tried. In terms of security, this solution is information theoretically secure. That's the strongest notion of security that it exists. It means that not even a quantum computer can break it. Actually, not even infinite power can break it. If an attacker compromises all aggregators but one, the information extracted is 0. The attackers need to control all the aggregators. I know that in this example it looks simple because I have 3, but I can have as many as we want. We can have 100 and we don't degrade performance. The only thing that the attacker can do is to tamper the shares of the aggregated model, but not in a smart way. So the attacker cannot introduce backdoors. It can only do additive attacks. So basically, it can transform our model into something useless. But we would notice. We would see that the accuracy is not converging, is dropping. The only problem is that we would never know who is the responsible, who is the aggregator that has been compromised. If we want to know who is the one that has been compromised, we need verifiability, which we don't have in this basic version of the protocol. In secure multi-party computation, you can have verifiability in many ways. And in PetalGuard, we decided to deploy verifiability in two different forms. The first one, we changed our underlying secret sharing scheme for another one called replicated secret sharing, in which we have to increase the size of the shares. So we are consuming more bandwidth. Also, the number of aggregators is reduced to only 3 or 4. Not more. If we go to more than 4, then the share size increases exponentially. And the trust setting also changes. Now, we can only accept one corruption. If we have 2 aggregators corrupted, we can already lose data. It is possible to get verifiability without changing the trust assumptions, but for that, you need communication between the aggregators. You need correlated randomness, and we didn't want to implement that for verifiability here. But it's doable. Another way, easy way to have verifiability in MPC is deploy inside TIs. TIs give you verifiability unquestionable, and the MPC protocol will give you information theoretical security for privacy. And I have been talking about private aggregation, but we want to do more than that, and PetalGuard will be capable of doing more than that. We want to do differential privacy on top of the aggregated model and model poisoning detection on top of the local updates without seeing these models, everything operating on shares. For that, we need secure computation. So we need to be able to run functions on secret shares. And we are working on that at the moment. This part is not just yet production ready, but it will be at the end of the year. For that, we require communication between the aggregators, but not communication of private data, communication of correlated randomness. This is something that adds up to the computational overhead, and so it takes more time, but fortunately it can be pre-processed. So you can have a pre-processing engine, like several workloads that are computing this correlated randomness, and whenever the federated learning process starts, you can feed it to the aggregators to speed up the process. This is what we are building up now. In terms of deployment, solution is fully Dockerized. We have a Docker container for the aggregators. We have a Docker container for the training entities. CUDA compatible only. Compatible with any model like CNNs, transformers, LLMs of any size. You can deploy aggregators and entities wherever you want, as many as you want. If you deploy them together, that means that the entities that train do not need to trust anybody because they already control one of the aggregators. We have tested already with LLMs. Our testing pipelines work with Falcon 3. We have also a graphical user interface that is very intuitive. You can configure all the servers. You can configure how is the data pipelines, how is the model that you want to fine-tune, what are the federated learning, the accuracy that you want to achieve in all your iterations. You can follow up how is the training process through an orchestrator. We are distributing through AWS Marketplace. So if you go to our web and click here, that will take us, will take you to our AWS Marketplace. It's listed there. We will also integrate with OPEC platform. So there will be a confidential AI platform that contains confidential federated learning. And as I said before, if you deploy the aggregators inside TIIs, you have verifiability without protocol costs. So it's a perfect symbiosis. And that's it. I would just add that we are working now on finalizing the part of differential privacy and model poisoning detection using secure multi-party computation. But at the same time, we started working on a more challenging task that is vertical federated learning. That requires other crypto primitives like private set intersection, for example. But that will be next year. That's it.